So I'm thinking that
Okay.
that vertical needed to be
Advantage with having the remote is I can stand
done
up
better.
and talk.
And it's not a big deal, but
Okay.
it's okay.
Ready to roll?
The next day I'm gonna drag
Yep.
on my stuff.
Okay.
Start asking
Well,
people.
good evening again, everybody. There's one or two new faces here that weren't here last time, but at any rate, last time I gave you a talk on a lot of the theoretical stuff and things you have to realize in order to do EME. Tonight, what I want to do is, okay, this does not seem to want to work. What am I doing wrong? Did you hit this? Is that the one?
No, you're hitting the wrong. No, I thought you did the right.
Didn't you unplug it?
No, I put it back in.
Oh.
There we go.
That wasn't
I like it better now.
It was working.
Yeah, I thought you worked it. Used it just a minute ago.
Murphy.
There.
It never wants to work when you... Okay, well, if it doesn't, I can stand here and flick it.
Just tell Chip to do it.
Yeah, I can do
You
it.
can do that too.
Next.
Okay, now it's really wanting to... It doesn't even want to respond to that. What's going on?
You can talk.
That's because the mouse is clicked up in the bar up on top, so it's trying to do that
You're
stuff.
probably right. Okay.
Can you turn that gun?
Yeah, that's in front of the camera.
Ah, yes it is. Sorry. Now let's just set it over here for now. We'll get to that a little bit later. Well, let's get this working here first.
She was warming this up.
Your screen sharing is paused.
How do we start it?
You still have the online people?
They're there.
Let me get in front of it. Sideways, it's hard to see.
Yep. No, please do.
And this is why dedicated task computers, when you're in an environment where people need to get something done, are important.
Well, I could have brought my own too, and I didn't tonight.
Hurry up, Chip, field day starts in 5 seconds.
Yeah.
Well down.
The local, I won't say locals, but the guys in Iowa work in Europe every day on 6. Not as far, Justin tries, but it ain't
Don't
happening.
save. There you go.
Every once in a while, a little bit of stuff will pop in, but it's been really bad
I
this
see
year.
Al's been banging on it a little bit, but I just don't see the good stuff. It was better a couple months ago.
Mhm.
I just quit.
Yeah.
Well, I'll be on this fall from my own house, so
I own red.
that 6-meter antenna will be up about 80 feet, and it's already.
Well, I'll go to his house. Yeah.
You know what, they did take good pictures of
Is that up?
And the people, you know,
Where, is that Victor says, is that what the hill?
It's on the next hill over, next hill to the south.
Yeah, fine.
And then the next hill to
There
the
we go.
south. from me.
Okay.
Yeah, they got good-
All right, now we're ready to go. Okay, tonight what I want to talk to you about a little bit is about actually building an EME station, what goes into it, and some things you got to take into consideration. And then the last part of this will be about doing some operating. I'll show you some of the stuff with my personal station and some of the experiences I've had. Okay, before we get too far into this, I did want to show this because as is the case on HF, you call most of the bands by their wavelength, 160, 80, 40. Well, the same is actually really true when you get up into the VHF and UH spectrum, but typically most people will call it by the frequency. When you get into EME, a lot of guys go with this, and I tend to go back and forth, so if I say something about 13 centimeters, or you see something labeled that's referring to the 2.3 gig band and so on. So if I say something or you see something, want a clarification, just let me know and we can continue doing that. Okay, well, the most important part of your system is obviously the antennas. Okay, and typically, if you really want to do anything serious, you got to run multiple antennas. Okay, and one of the things that's very important is knowing the proper stacking distance. Most of the manufacturers will, sorry, wrong one, really one. There we go. Okay, you'll usually see stuff like this. Now they don't always put it quite this clearly. And you'll see here, this one is 14 feet high and 14.5 wide, and where that actually comes from, I've also highlighted this, is the beam width in the E field and H field. Now, let me just tell you a little bit about what that means, just because when I show you the next slide, you'll understand why it's important to know what that means. Okay, all the electromagnetic waves that comprise radio waves have an electrical field component and a magnetic component. Okay, E is the electric and H is the magnetic. And they're showing the beam width here in those two fields, and what this is it's the 3 dB down point or half power point. If you had the plot with all the circles on it, you go to the first one where it says minus 3 dB, and you look at the spread where the wave crosses that, that'll be your 3 dB down point. Okay. Now the E field, it's important to know which is which. You'll see that when I show you the next slide. But the E field, or the electric field, is always going to be in the same plane as the elements. So if it's horizontally polarized, your E field will be horizontal. If you're vertically, it'll be vertical. Okay, the magnetic plane is always going to be 90 degrees off. So if you're horizontally polarized, your H plane will be vertical. If you're vertically polarized, it'll be horizontal. Now I wanted to show you, this is why I wanted to kind of explain that. You notice here, it's showing the stacking distances, but he's just saying E plane, H plane. Well, which is which? Okay, well, the way I remember it is E for element, E for electric. They're going to both be in the same plane. So if you're horizontally polarized, this is going to be the horizontal spacing. This will be the vertical spacing. Okay, and you notice this one is different. Well, that's because this has wider beam widths. And the wider the beam width, the closer you space them. I'll show you in a few minutes a couple of formulas that are used to get to this.
A simple question.
Yeah.
Why is magnetic H instead of M?
I don't know. It's just why is electric, electric is E instead of volts,
Yeah,
so
okay.
instead of V for volts, so same thing. Okay. All right. I looked on the internet to try and come up with something to show you how they arrive at these spacings, and I found actually 3 different formulas. This one here is pretty old, the top one. DL6DU, he did an awful lot of antenna work probably back in the 60s and 70s. And he came up with this, where the stacking distance is equal to the wavelength that you're operating on divided by the quantity of 2 times the sine of the beam width at the minus 3 dB points. And note here is that whatever you put this in, it could be wavelengths, it could be meters, it could be feet, whatever. Whatever this unit is what this unit is. Okay, I found this one, this is from W6PQL, and he says, oh, what most guys do is use this. It's the distance is equal to 57 divided by the 3 dB beam width in degrees, and this is in wavelengths. So you have to convert that to meters, inches, whatever you want to come up with it. I did find another one online that was a modification of this. The guy said 51 divided by this. And I'll tell you right now, I took and plugged numbers into all 3 of these formulas, and none of them came up with the exact numbers that you see on either of these. I came close, okay? It was within a few inches. So I'm suspecting what they're doing with the manufacturers, they're actually using computer modeling and getting it a lot more exact. They're probably coming up with a number that's like 31 point something, 33 point something. And then for wavelength, are they using 2 meters? Are they using what the wavelength is at 144.2, which is going to be like 2.08? I don't know exactly how they're doing it, but typically you don't have to do it on your own, but the big thing is just knowing which plane is which, okay, in case you run across that. Okay, moving on. Okay, the other thing you run into is when you start putting resonant antennas together, you start affecting the resonance or the impedance of the stack, all right? If you put 250 ohm resistors in parallel, what do you get? 25 ohms. Well, same thing happens if you put 250 ohm impedances in parallel, which is effectively what you're doing. You're going to have 25 ohms here. Okay, well, what happens if you hook a 50 ohm transmitter to a 25 ohm load? You're going to see a 2-to-1 SWR. Okay, you go to 4 antennas and it gets worse. And you can do this two ways. You can do it with coax. The thing with doing it in coax, especially this one up here, these have to be odd multiples of quarter wavelengths. Okay, it's the quarter wavelength thing is the transformer part of it. Okay, well, a quarter wavelength at 2 meters is what, about 18 inches? And if you got to stack these 14 feet apart, you got to come out the boom and stuff. I mean, you're going to have obviously a lot more than 18 inches. But the key thing here is you have to figure out what's a multiple quarter wavelength, cut it to that length. Now the other thing that's important is the antenna's got to be fed in phase. So that means these have to be the exact same length. Same thing down here. These have to be exactly the same, and these two have to be the same. Okay, these two don't have to be the same as these, but they have to be the same, and these are actually quarter wavelengths. These don't have to be. Okay, this is done a lot on 6 meters, and I've seen a lot of the guys that are running these great big huge arrays will do this, and what they actually do is they don't even use the connectors and the T's. They'll run 3 coaxes up like this and trim back, and they'll solder the braids together, bend the center conductors from the 2 outer ones to the center feed, and solder them and weatherproof them. And that works, but the key is you got to weatherproof everything. But you're putting up an array of 48 antennas. That's a lot of connectors otherwise. Okay, preferred way, and the way I do it, which is more common with smaller systems, is to use a power divider. That's what these guys are. I'll pass them around if you want to look at them. Okay, there's quarter wave ones like these, and this is actually a half wave double one for 1296. Okay, and the thing with that is, you know, they call them power dividers. Essentially what this thing is an impedance transformer. Okay, and like I said, you can do quarter or half wave. And the important thing here is your transformation is done here in impedance. So these lines can be any length. Now, they all have to be the same length, but there's no requirement that they be a multiple of a quarter wavelength. Okay, and well, you're seeing stuff that's coming around. Here's the 2 here on the bottom are quarter wavelength for 432. This is a 2-port and a 4-port. This is a half wave unit for 222. Now the thing with a half wave is it's actually 2 quarter wave sections back to back, which effectively puts them in parallel because the feed point is here in the middle, so you got a quarter wave here, quarter wave here. Doing that though does affect the impedance of the line in there, and I'll show you that in just a minute.
So Charlie, on the
Yeah.
2-port, does
Yep.
it transmit half the power out of one port and the other
Correct.
half the power out of the other port?
Correct.
At the same, so it's the right angle for all the
Yep.
waves that are being?
Yes.
Okay,
Yep. And this one will divide it in 4.
okay.
Okay, same thing here.
So it's less power on
Well,
each antenna?
On each antenna, but it's all combined together in the end.
Okay. And the antennas are really quite narrow on the beam?
They typically tend to be, and then they become even narrower when you put them all together.
Okay.
In fact, if let me back up just 1 second. I don't know how easy it is to see, but if you look at this M² one, they actually show a radiation pattern over here. This is for a single antenna, that's for 2, I'm assuming stacked vertically. You notice when you get to 4, it gets really, really narrow. But your gain goes up, but the overall beam width is going to narrow down. Okay, let's get back where we was here. Okay, and this is basically how the thing works. It's an open air transmission line, quarter wavelength long. The way the impedance is set is it's a ratio between the inside diameter of the outer conductor over the outer diameter of the inside conductor. Essentially what it amounts to is the space between here is what comes up with the impedance. Now there's a formula that you can use to figure out what impedance you need to match. Now this particular one, a quarter wave 4 section, you're going to have 12.5 ohms basically here, and you want to match it to 50. And I think if I remember right, the formula is something like the square root of the this impedance times this output impedance. And for 12.5 ohms, you come up with a 25 ohm line is what you need. A 2-port is gonna be 25 ohms, and I think the impedance match, it turns out to be something like 35.5. Down here is the half wave. Well, first of all, let me back up. If you use this, they're using a 1-inch diameter square tube with 1/8 inch walls, so they'll give you a 3/4 inch inside diameter of the outer. And if you go through the formula, what you come up with is a 1/17 32 inch brass tube, which they are available, will give you something real close to 25 ohms. Okay, now if you go down to the 4-port, one thing I want to point out here is the first thing you notice, okay, this is also 4 ports, but it's showing a diameter of 11/32 for the inside one. So obviously, this is not 25 ohms. And the reason being is, as I mentioned, you have 2 quarter waves back to back here. Okay, so effectively, this line is in parallel with this electrically. And if you actually do the math, this comes out to be about 70 ohms, 70.7. Well, what you need for a 2-port, and that's really what you're designing for here is a 2-port, is 35 ohms. Well, 70 in parallel with 70 will give you 35. That's the way you do it. Chances of building these, I've never built one myself, I usually have bought them, but you know, if you ever do that, just bear those things in mind. Okay, I want to just touch real briefly on dish feeds, because we'll talk about dishes a little bit in this. There's typically in the ham world about 3 different ways to feed them. Some of the lower frequencies, like 2 meters to 432, if you're using the dish, they typically use a dipole feed. And they're linear, so what they typically will do is put a rotator of some sort on the feed so they can spin it to change polarity. I have seen pictures of small Yagis with that actually they aim out to a reflector that beams back at the dish. They have sometimes been used way up in the upper spectrum, but I haven't seen too many of those. Patch feeds are typical. At least like at 902, and actually I've seen patch feeds at 432. They're fairly easy to make and relatively small. What's most popular when you get to 1296 up is a waveguide feed, or really what's really become popular is this septum feed. It's nothing more really than a waveguide in its own right, but it's got a divider down the center. This was developed by OK1DFC, and it's become really widely accepted. Here's just some pictures that I found. This is an example of that dipole feed in front of a reflector, and that'll be put up so this will face, the dipole itself will face towards the dish, and this will be behind it to reflect any signal that comes out back to the dish. Okay, here's an example. Whenever I hear that, I think it's my phone, sorry. Here's an example of a patch feed. This is one I built for 902. This is the first one I built. The 2 connectors are mounted on the back and come through and solder here, and this thing is raised, it's like 10 millimeters off of the back plate. This was supposed to work at 902. I did not put any tuning stubs or anything in there, and it didn't work, and when I got a VNA input on there, it was actually tuning up at 930. And the SWR was really out of whack down at 902, so I ended up throwing it away and built a second one, and I followed W5ULA's recommendations and put the little tuning discs and stuff in there, and it tuned right down to 902. It works great. Here's an example of a waveguide feed. That's this one here. I'll pass this around. This is a complete feed that I was trying to put together for 10 gigs. And then up here is an example of the septum feed. This is one I built for 2.3 gig. I have one on 1296 that a friend of mine built, and right now I'm in the process of putting one together for 3.4 gig. Okay, it's essentially a waveguide because you've designed it such that the opening here is just below the cutoff frequency where you want to operate. The thing that makes it different is there's this divider that's put in between the 2 pieces, and it's stepped like this, so it steps up. I don't know exactly the physics of how it works, but it creates circular polarization, I can tell you that, and it works really well. The other thing that's neat with this is there's 2 separate connectors. There's a transmit and a receive connector. The other one is on the opposite side. It is important to hook them up correctly because depending on which one you use for transmit will determine whether you're doing circulation this way or circulation this way. And if you go the wrong direction, it's like this versus this on Yagis, and you don't hear anything. And I made that mistake on 902, so I know it doesn't work.
So where does the RF enter that? In towards the,
And this,
yeah.
oh, sorry,
Receptive,
back
yeah.
up. Come on. The connectors are right here.
Yeah, but the feed is on the other
So you're
The
pointing.
open end of the wife guide is
Okay,
here.
gotcha.
Okay, the feed is here, there's a little probe that sticks in, and then these
Yep.
are for tuning. You run a bolt through with a disc on it, and you tune that in towards
So the dish is sitting at,
the dish will be out here.
gotcha, okay.
Okay, you'll see it when we get to, later in the presentation, I'll show you how it's mounted. And then the other thing that's typical is that there are, when you build these things, there is, when you power them, there is some lobes that form that kind of want to come out this way. And what they usually do is you put a choke on here, which is a scalar ring or multiple scalar rings, and that'll reflect the stuff back. And I'll show you an example of that when we get a little bit further in. Okay, next thing is, if you want to do more than just a few degrees at moonrise or moonset, you really need to have an elevation system so that you can track the moon all the way across the sky. When I got started back in 1993, these were basically the two things that were available commercially. Keep hitting the wrong buttons here. This is a Yaesu G500. I think today it's a 550. It's really intended for satellite antennas. It's very light duty. But back in '93, that thing with the controller retailed for under 300 bucks. Okay, and it was affordable. The other option at the time was this contraption here that's made by M2. Really, really great heavy duty thing. I did find a picture online, but the drawing is actually better because the picture was at a weird angle. The one thing this doesn't show is the way this works. There's actually a piece of roller chain that's fastened here, and it comes down and runs through like this and then up the back side. So when you run it, that chain runs and it turns this whole thing. You mount your cross boom across here, and it'll take up to a 3-inch cross boom. They actually even made brackets that you could mount a Roan 25 tower section on there for a really big array. Well, back in 1993, this thing alone, without the control head, was 3,000 bucks. I didn't have that kind of money. I was on a really tight budget. By the time you added in the controller, it's at least another $1,000. These days, it's about $6,000. The prices have just gone out of sight. So when I put up my first array, I broke down and I bought one of these because it was easy. It proved very quickly to be inadequate. I had it up for 8 months and I had so much trouble that I had to come up with something else, and I still couldn't afford this guy. So what I did is I built my own with an actuator arm. I know there's a lot of guys who use arms. I didn't really have any details, but I did find, and I can't remember where I found it, but I can't really take credit for this design too much because I did find somebody else that had described this actually for satellite use. Okay, and what it consists of, well, here's your actuator arm, okay, and on the mast, you build this plate. It's 1/4-inch steel, and you mount these pillow block bearing units like this, and then the bore on these bearings is 1 inch and 15/16, which turns out is almost an exact perfect fit for 1.5 inch Schedule 40 water pipe, which is what I'm using as the cross boom. Okay, and then you mount the fixed part of the arm here. The trick is coming up with this length, and I just used some geometry here as a right triangle, and I came up with something that actually turned to be pretty close. And when I got this all put together, I found I had to play with the position of this up and down a little bit, because what you find is if this distance is too short or too long, or this is too short or too long, you end up either not getting enough movement to get your full elevation, or you get full elevation but the steps are so coarse that, you know, instead of like a degree or 1.5 degrees between steps, you'll end up with like 5 degrees, which on 2 meters really doesn't matter, but when you get up higher it does.
Well, the arm slides and the clamp and the whole thing hits the ground. I've had that happen with dishes.
Yeah. Well, the thing with this, now, I'm at about 45 degrees where this is taken, so this is straight out. When you're down at completely zero, this arm is actually going to be tilted like this, and the back end of the arm pivots here when it moves. So when you're down at zero, the back end of the arm is actually up here, and as you raise it, the arm moves down this way.
Is that a 36-inch arm?
This one is 24.
24.
It's a 24-inch Super Jack. On my other array, I have a 36. And what happens there is you have to make this different. The length is different. This thing works great. And I think when I built this, it cost me 110 bucks for the bearings. I bought them at Wisconsin Bearing in Eau Claire. You know, they're high-speed bearings, but they turn a quarter turn and they aren't high speed, but it's what I could get. When I built the second one of these, I found the same thing on eBay. They're Chinese made, but I got the pair for 35 bucks. Okay, and I bought the plates over at Steel Town, and that was like another 30 bucks. The arm I had a friend at Cray named Mark Olson. He lived up in Bloomer. He eventually became N0AKC for a while, but he's let his license lapse. But
I'm working on them.
you are, okay. You know him. Good. Mark's a great guy, but he's the one that machined all this stuff out for me. He got this big block of aluminum, and he had access to the model shop in the engineering building. So he milled all this stuff out, and this is actually split, okay, with cap screws here to tighten it. And he actually, up here, this piece was actually sawed off the top. The problem here is, as you can see, the screws are on the back side, okay, and they're cap screws, which takes an Allen wrench. You really can't get enough torque on these. I always had trouble with this thing slipping, so I used it for a while and replaced it. If you got any question about just how much force this thing has, I'll show you a picture here in just a minute. But first, I want to show a couple other things. This is the control head down in the shack. It's completely manual. This doesn't have, it's an old power supply from a really old satellite, C-band satellite system. The thing I like, and this is something I had, and I have since picked up a couple more on eBay for like 25 to 30 bucks, 40 bucks, somewhere in there. The thing I like is it's got this 2 digital readout that counts up and down as you move the arm. Unfortunately, it doesn't display degrees. Okay, it counts pulses, and as it gets so many pulses, it just increments, and I think it goes down as far as 10. And if I had a big enough arm, it might go as high as 99. I don't know. But what I ended up doing is I created this little chart here. Okay, the red numbers correspond to this. The black numbers correspond to the elevation in degrees. And this is actually the chart for the 222 for the 432 with a 3-foot arm. And I can get 74 degrees out of it, which is about the max you ever see here for moon elevation. The one on 2 meters, I can get about 80 degrees. The problem is you tilt it. When I get to 80 degrees, the arm hits the top of the tower, so I can't go any further. Okay, well, here in Wisconsin, you get some really ugly weather, okay? And I want to show you this for 2 reasons. One of the things is when you mount these things, you got to try and balance these antennas. Well, with the modern designs, the balance point isn't in the center of the boom, okay? Because you actually have more elements behind than you do out front. Plus, you also have to take into account your feed line. Okay, so you're going to actually mount a foot or 2 back. And this isn't actually perfect, it's a little bit front heavy. Well, the problem is you start getting snow and stuff built up on like this, they get really, really front heavy. And this was in December of 2022, and we had that 12 inches of really wet, heavy crap in December. And these antennas were all fully caked like this. My 2-meter array looked the same way, and I got nervous because these booms were really sagging, despite the fact the guy wire up here on the back one on the 221 broke.
Are you using fiberglass then?
No. You don't. You wanted to use fiberglass if you're vertically polarized. You don't need to on horizontal. Okay, because there's so little interaction with boom, or with the elements, that it doesn't really matter. It is a bigger deal when you're vertically, because now your elements are going to be blocked. Okay. Whole half of the elements blocked. Okay, so there it becomes important. I'm just horizontally polarized. Well, you can see what happened here when I tried to shake snow off of these things to get the booms to straighten out. I shook it off, it ended up coming off the back. And it got so front heavy, the clamps couldn't hold and it just spun. And here's the 220 on this side, that was actually worse. Well, the 2-meter array looked just this bad. I don't have a picture of it, but I made the mistake of trying to elevate it so I could get at the back of the antennas. Well, there was so freaking much weight, it was so out of balance. I think first the clamp slipped, and then it got to the point that the arm started pushing that arm sideways. This was the end result.
Yikes.
It bent, and I was really worried because I'm watching, it's not moving, but it's counting. It's what's going on. So I stopped, I walked out and looked and found this, and thankfully it didn't bend the actuator. That survived. But if you got any doubt about how much force you can exert with that thing, here's proof. Okay, I did manage. I had to heat this thing up and I straightened it, but that was something else. Let me tell you. Okay, well we've completely covered all the antenna stuff here now, so I want to show you a quick block diagram of what the rest of the system looks like.
Probably have to put a smudge pot underneath it, just keep it thawed out.
Well, the thing is, you learn that, okay, it looks bad, but they ain't going to break, you just let them thaw. In a few days they usually do.
Yep.
Unless the wind comes.
Well, and that was what I was worried about. But the nice thing is, with the EME stuff, it's only 20 feet off the ground, and I got trees all around me, so it's pretty protected. I'll tell you a story. When I first put up my first array, a couple nights later, we had a horrendous windstorm, and I was awake all night, figuring for sure that tower was going over. Didn't move an inch. Okay, block diagram here. I mean, obviously you got your transmitter, and it can either be a transceiver or an IF radio with a transverter. All of the things I'm doing right now, I use this method, and that's mainly because when I got started, most of the all-mode radios really weren't very good on CW and sideband. Okay, so by going this route, you actually get all the features of an IF radio, which typically had much better selectivity, much better sensitivity, and all you're doing with this is converting the frequency up and down. Okay, so it's really, this is your radio, and everything it can do, you can use. Okay, and then from there you go up to the amplifier. Okay, and then you go up here, and note that this says everything in this box is at the antenna. Well, this is your low noise receive amplifier and your fail-safe bypass relays. Okay, because what you want to do when you transmit, you need to switch the LNA out, because really there isn't anybody that makes one that automatically switches to RF. There's one manufacturer I know of that made one. That's Advanced Receiver Research. But they're only good to like 50 or 100 watts. They're made for satellite use, okay? They can't handle the powers that you're running at EME, okay? So what you need to do is when you transmit, you switch this out and you hook straight to the antenna, okay? On receive, you put this back in line and you come back through this way. Now note that I show here this dotted line that shows RX and this one TX, and yes, that means 2 separate feed lanes. Okay, you don't have to do that. I do that, and the main reason is it makes this much simpler. Okay, with 2 feed lines, you need 2 relays to adequately protect. If you go this route with a single, it takes 4, and I'll show you that in a little bit too. Okay, now I want to point out this little box here, because this is something most of you probably have never seen. Okay, it's called the sequencer, as you can see in big letters, and what this does is it runs off of the PTT from your IF radio, and when he transmits, he runs through these events and turns things on in a specific order with a delay between each stage. Okay, and it stays up as long as you're keyed. When you unkey, it turns everything off in reverse order. Okay, the sole reason you use this is to protect this. Okay, you don't want to hot switch relays, because you'll burn the contacts, and if you're running 1500 watts at 2 meters or 432, you don't only burn them, you vaporize them. They will literally disappear. Okay, and those relays can be pricey, so you don't want to do that. So you got to turn everything on and off such that you make sure that before RF gets up here, this thing has completely switched. And same thing on receive, you make sure that all the RF is gone before you switch back.
So
Okay.
if you're doing Morse code, do you like set the delay so you don't kick back and forth?
What I always did was I keyed the microphone that held it firm,
Okay,
and then I'd send with the other hand.
because you don't want to go back.
I don't want it should still protect it, but I don't like doing that, and I sometimes will get a delay in there, and what it ends up happening is the first character you try and send keys everything and you miss it, it doesn't get sent.
Yeah.
I had guys I was doing it the other way at first, and I had guys telling me, I don't understand what the hell you're sending me. So when I started keying the microphone to hard lock it into transmit, then that went away. Okay. The one thing to point out, the way I set mine up here is event 1 runs the power. I turn the power off during transmit. You don't necessarily have to do that. In fact, for a long time I didn't, but it does afford just a little bit of extra protection. And I found out a lot of guys do it because in some cases they had LNAs that when they switch it, they started oscillating, and that prevents it by turning it off. Okay, the other thing reason you put a delay in here, okay, this relay is a mechanical switch, and every mechanical switch there is suffers from a phenomenon known as contact bounce. Okay, and what that is, when that thing closes, it's got so much energy, when it hits the contact will actually bounce off and sit there and oscillate for a short period of time until it settles out. In a relay, it's typically 20 to 30 milliseconds. But still, while it's doing that, you don't want to be applying RF, because again, you could be open or closed. So you make sure it settles all the way out. Okay, so first event, power. Second event turns the relay. Third event pulls the PTT line down on the amplifier. And finally then you key the transverter. Now the thing to bear in mind is as soon as you key up the radio, it starts producing RF. But nothing comes out of the transverter until PTT goes low. Okay, and that's the last thing to happen. So all this should be switched and settled down. If you go with a transceiver, okay, and one other thing, I run all my amplifiers as just a pass-through amplifier. I don't TR switch in there, obviously, since I have a separate line. If you go this route and you use a radio, you got to be really, really careful, okay? Because if you got a TR switch over in the amplifier, okay, it's not going to key and switch until he goes low, which is event 3. Well, if this guy produces RF right away, boom, it's up here before you get through this sequence and you blow the preamp. They can't handle more than a couple of milliwatts going through them. So you got to be really careful with that. You know, if you do there are ways to do it. I don't want to waste a lot of time showing you how, but there are ways to ensure that that doesn't happen. Actually, one of them is in WSJT. There is a delay you can set in there that holds off actually sending audio. So you'll key things, but there's really no transmit power goes out until that delay, and you set the delay up so it exceeds, you know, the 4 events here. And here's a typical sequencer. It consists of 4 comparators. Okay, and let me point out this particular one is made by Down East Microwave, and this is a very, very old thing because it says Frenchtown, New Jersey. They relocated to Florida about 15, 20 years ago. Tells you how old this is, but they still sell this product, or a version of it. But you got 4 comparators, okay, and using the power supply and this resistor divider network, you set up thresholds on one of the inputs here. Over here you have a capacitor RC network, okay, and you also have this transistor switch. The way this works, okay, when you're not key down, this transistor is on, so your current flow from the supply goes through here. Okay, and any residual charge there might be here is going to discharge back through the transistor. Okay, well, when you go to transmit, you pull this low, this guy shuts off, now your current path is here. Okay, and you start charging that cap. Well, that cap is hooked across the other input of all of these comparator stages. And what happens is, as he charges, first it's going to pass this threshold, turn this guy on, which turns on this relay that will send power or remove power from your LNA. Okay, a little bit later, as this charges further, this guy turns on, that runs your TR switch, then this guy will go, and that's your amp, and finally this guy, which is your transverter. Okay, and as long as this is down, you're going to have pretty much full voltage sitting on that cap, so these will all stay on. Okay, now as soon as you unkey, transmits over, you unkey, this guy turns back on, and now you start discharging the cap through there, and now you do everything in reverse order, because this is the first one that will fall below the threshold and shut off, then this, this, and this. It's actually pretty simple, and an awful lot of the sequencers you find are built this way. Now I've got one that I designed, let me see if I can find it here. Actually, I want to show you too. I actually have an example of the down east one. I'll pass this around. This is the down east unit with all the big relays and stuff in it. That's wired up for my use. I designed this little guy here that's based on a microprocessor, and it actually replaces all this stuff. And you set up the firmware in here with two counters. The first one is the delay counter between stages, and then the second one, okay, when this guy goes, he counts, then this. So it just does everything with a couple of timers. The advantage of this is it's really little. Okay. Pass that one around.
So what is the transverter doing with that power that's being pumped into it?
It just absorbs it.
So what if you were running, okay,
A transverter typically only takes a few milliwatts in,
yeah,
and if you're running more than that in, there's an attenuator in there. So it's just a big 50 ohm resistor. So and you're only holding off for maybe 100 milliseconds. It's not a long period of time. So it'll take it. Okay.
there's no way at the radio to have the push to talk and then have the amps come on later,
Well,
not without modifying it?
not without doing a lot of modification. Okay, this is a simple and easy way to do it. And these things aren't very expensive. You buy that kit from down east, it's like 40 bucks. And I think I built my little one for about 20. Of course, I had to get the boards made. This is a timing diagram that just shows how this works. And now notice here that I've got this set pretty wide. It's 250 milliseconds between steps, so this is showing a 200 millisecond delay between stages. I think I've got it set now that it's like 25 milliseconds. It's a lot shorter than that, but anything, you know, from about 100 up to about 100 or 200 milliseconds for the entire thing is more than adequate. Okay, but you see how this works. Okay, PTT goes down, event 1 goes, you know, delay time later, event 2, same delay, event 3, event 4, they stay up till you drop PTT, this guy shuts off, followed by him, and him. It's really simple the way it works. Okay, now after showing you all this, what I'm going to tell you is typically the first two you either invert, or if you're running a relay out there, you use the normally, gotta do this right, the normally open contacts for receive. Essentially what it amounts to is you want to, instead of the normal thing where the normal transceiver or amp, you energize the TR relay to transmit. Here you do it the other way. You energize to receive. And there's a legitimate reason for doing that. The reason being, okay, when you're receiving, okay, obviously your preamp is connected to the antenna. All right, and if you energize the transmit and de-energize your receive, what happens when you shut your system down? You leave the LNA connected to the antenna. In addition to power, they don't like lightning. Okay, and you leave that thing vulnerable to getting blown up if a thunderstorm comes over.
Ever have one that just wind static took out?
I have not, but it can happen.
I thought
Okay.
I'd heard of it, and I was wondering if
Oh yeah,
had
it does happen. It does happen. And you don't have to have a direct hit of lightning either. Just the fact that lightning will induce charges and stuff, and that can be enough to blow it. So essentially what you do is you power this guy the opposite direction, and then obviously if you're using this to control power to the LNA, you got to make sure it's powered when you're receiving and off when you're transmitting. But you either, with mine, I've got a little dip switch on there, and that's used to select the inputs you want to reverse. So you actually have them powered up, and when you go into transmit mode, you turn them off and you turn the other two on. On the down east one, he doesn't have that selection, but he's got both the normally open and normally closed contacts available out at the relays, and you just choose the one that puts you in the right mode. Of course, then you got to make sure you go out and turn the relay around too, and use the normally open contacts for the receive side. Okay, I'm apologizing, this has taken a long time, and this is a fairly long presentation, so we get partway through this. If you want to stop, we can, or I can try and speed through it or skip part of it. This is some examples of some preamps that I've got. I've got, I think, one of those here. It's not one of these, but this is one that I built for 2 meters, way the heck back in the 90s. And there's a note on there from V7BQH. He actually tuned the thing up for me to set the noise figure.
What did you end up getting for a nice figure on there?
On that one, what does it say?
0.35.
0.35.
Oh, that's pretty good.
It was actually pretty darn good. I think that used an was it MFG or MGF 1302? It was real common back then. They're long since gone. Okay, these are the ones I'm using on, well, 13 centimeters. That's 2.3 gig and 23. These are dual stage. This guy's getting 26 dB at 0.5 noise figure. The 1296 one is really awesome. It's 0.35 or 35 dB at 0.27. They really work really well. I mean, they're expensive. I think I paid about $200 a piece for these, and I just today ordered one for 3.4. But they really work and work well. Okay, and they're really solidly built. I inadvertently applied 24 volts to them once, and I thought I blew them up. I didn't. The down east ones, if you did that, they're gone. Okay, this is a down east dual stage for 10 gig, and that's actually on this guy right here. Okay, and down here are a couple of different ones that I've used on 70 centimeters. This is the current offering from down east. This was an older one. It's just different FETs inside of them is really what it amounts to. Okay, and this is what the inside of that 10 gig looks like. Very simple. I mean, here's your RF path. Comes in, you got the 2 stages of gas FETs and 3 capacitors. That's it. Okay, obviously no switching. All this stuff up here is power supply and biasing for these 2 guys. And they're really simple devices, they really are. Okay, now we come to how do you set up the configuration. Now, I'm going to admit I stole this diagram from KL6M. He's got a really nice paper he wrote up on this whole process of the various configurations and how you switch things and stuff. And I'm going to try and go through quickly what he described in about 8 pages. He's showing 5 different configurations, and remember I told you that properly you need 2 relays with 2 feed lines and 4 with 1. Well, he's only showing 3, but we'll get to this in a minute. These are other possible configurations you can build, but they are very highly unrecommended. Okay, the reason being, well, first of all, you notice everything is saying high power up here. That relay has to be able to withstand whatever your transmit power is. So if you're running, a kilowatt, 1500 watts, it's got to be able to handle that. They're typically a more rugged and more expensive unit. Okay, when we get over to isolation relays, they don't really handle power, so they can be a lot simpler, cheaper relays.
So are they vacuum relays then?
The ones, some of them, what I'm using are, and I'll show you an example here in a minute. Most of what I'm using aren't. They're just the mechanical coaxial switches. Okay, now the reason you don't want to do this, okay, believe it or not, well, what it comes down to, okay, this guy will have some leakage from port to port, from here to here during transmit. There's some intrinsic capacitance in the thing. I mean, it's part of physics. You can't change it. It's probably only a couple of picofarads because it's an open air dielectric capacitor between the 2 relay contacts. At DC, it's going to be infinite because capacitors don't pass and an open circuit doesn't pass DC. You start applying RF to it, that changes. Okay, and the higher you go, the worse it gets. Okay, and now Mike was on and he says, okay, well, we know these don't handle a lot of power, but what can they really handle? He says, that's something that's really debated a lot, and he says it's a really good question. His comment was, let's set the benchmark at 0 dBm, which is 1 milliwatt of power. Okay, well, if you're transmitting a kilowatt here, that's 60 dBm. So this guy has to provide 60 dB of isolation. Well, at HF you might get close, especially the low end of HF. At 2 meters, most of these are going to come in at 30 to 35 dB. Well, a kilowatt at 35 or at 2 meters with 30 dB of isolation means you could have up to a watt of power sitting here. And that gas Betz going to do this the first time he sees it. It ain't going to like it. Okay, so that's why you don't do this. This is an attempt at a single feed line, but it's just as bad, and in fact it's worse because you also are now putting potential power on the output. The output will handle more power, but it's still limited what it will take. And will it handle a watt? I don't know, maybe. It's probably going to last longer, but it's really not a good thing to do. This is what I do, and this is probably the most common. You run 2 feed lines and you insert what's called an isolation relay in here. Okay, now your isolation from the relays is the cumulative of both of these. So if you got 30 dB on each, that's 60 dB of isolation. The other thing you do is when you go to transmit, you actually switch a terminating resistor on the front of that. It gives you more isolation. It's going to dampen out anything that it might get through to it. It's just a 50 watt or 50 ohm resistor. Usually you can get them in a coaxial type mount, a connector type mount. Now this is his version of a single cable system back. The thing I don't like about this is he ain't doing anything here. Okay, and I told you it takes 4. What's typically done in this is you insert another isolation relay here. Same thing with a resistor. So when you go to transmit, you completely isolate that LNA, and you won't have any problems. I've never blown one other than when I've left it on during a lightning storm and forgot to shut it off, or if I've had a relay failure and you pump power in. And trust me, if you put 1500 watts into one of these, the circuit boards in there turn black and you vaporize foils and everything. I mean, it just literally destroys them. And Mike shows this 5th one here. And I mean, it's basically 2 feed lines to the shack, and what he does is he's kind of isolating the amplifier into this line only, so it doesn't come back here. This I could see working, but to bear in mind, if this is a tube amplifier, you might be running 100 watts of drive. So, I mean, you still could be getting, 100 milliwatts or something back here. Maybe that'll damage it, maybe it won't, but I don't know. I don't see the point of this, really. Okay, and here's an example. This is my relay box that's up on my 222/432 array. Now, this has got 2 separate systems in it, because I'm 2 bands. These coaxes up here are my transmit lines coming in, okay, and this is 432, comes over to this relay. Now, Brad, you were asking about vacuum relays. That's what this one is. Okay, it's an outfit made by Downey's Microwave. I'll show you a picture here on the next slide or two. It's a nice vacuum relay that he makes. It's good to full legal limit all the way up through 432. I've bought a couple of these and used them.
Expensive, though, right?
Right now they're going for $215. They're not cheap.
So the vacuum part is the contacts for the vacuum?
Inside of here is a little vacuum relay module that's in here, and then he just solders it up to the connectors.
So, but the vacuum is the contacts?
Yes. Yeah. Okay. All the rest of these are just standard coaxial relays, and I actually have all high power relays in this one because I wanted stuff with all end connectors. But the output of this, that goes to the input of the isolation relay, 50 ohm resistor right here, and the output goes to the preamp. This is the 432 preamp, and this is another one made by WD5AGO, and it actually has a cavity filter on the front end. I don't know if I really need that, but there were some other things about this guy I liked, so I bought that one from him. I think that one set me back about $250. They're not cheap, but they're very high quality. Okay, and then the 222 one, here's the main TR relay isolation, and the preamp's actually here. And by the way, the common relay or common port on this guy is actually feeding out the back of the box to my power divider. Okay, if you're wondering what these guys are, well, I actually have 2 stages of preamps in this design. The reason being, you can see the house back here, that's where the shack is. I've got about 180 feet of feed line here. And DK3WG told me that this is the way he does everything. He runs dual stages. That way, he said, I can use RG8 as my receive line. He said that you can run just about anything because you get so much gain here that you're gonna more than make up for the line loss. I get about 40 dB of gain here between the two stages of preamps.
So one feeds the other? Or
Yeah.
how's-
Yep, yeah, the output of this one feeds into here. Okay, and then here's the output port. This is the feed line back to the shack for receive.
So
Same
that
thing here.
offsets the additional noise in there?
That's kind of what this is for. I mean, if you got any IMD products or things, it's supposed to eliminate them. I don't know that I have any, but there was other features about the thing I liked. Okay, and here's some examples of relays, and I think I got some, but rather than pass them, let's just keep going. This is a high power one. These are all lower powered. These are typically what I use most of the time for the isolation relay. They don't have to handle hardly any power. I mean, other than maybe a watt or so. So you can get by with a lot less. These are all surplus. I bought at flea markets and stuff. You used to be able to find these things for 10, 15, 20 bucks. Prices have been going up because they're getting harder to find. Okay, here's this down east stuff. This is the one that I showed you, Brad, that I'm using. Okay, it's a single pole, double throw, typical thing. He also makes this. Okay, and this is actually a combination of two products. You can buy just this box, okay, which has actually got 4 relays in it. This is your single cable solution. Okay, and if you buy just this box, there's another connector out here, and typically these are N's, not SMAs. This particular one, he's actually joined a preamp up to it. So basically, if we go back, it's giving you this complete solution here with the 4th relay in that little box. Okay, really nice. Unfortunately, this thing goes for 525 bucks. Well, if you're buying new and you buy 2 of these, you're almost to that anyway, so if you really want to go with a single feed line, you know, it's not a bad deal. I think without the preamp on it, it's $475. They're not cheap, but you know, that's the way it is. Here's some examples of transverters. Okay, this is an old unit that they're no longer in existence, but when I first started on 2 meters, I had one of these. It's made by a company out of Liverpool, England, called Microwave Modules. They've come and gone. They were built back in the 70s and early 80s. They made units for 2 432 and 1296. The 2 meter one I had took like 5 milliwatts in and produced 10 watts out. I mean, there's a local oscillator in here, and you mix it with your IF, and you take the sum going up, do a little amplification, and then on receive, you bring in the RF, mix it with the local oscillator, take the difference, which is your IF. That's how the things work. They're quite simple. Okay, this unit and this one up here, this is front and back. These are made by Down East Microwave, or I should say were. Down East is still in business, but about 10 years ago he split part of it off to another company. So now he's only selling stuff 2304 up through 10 gig, and I think he's working on a 24 gig system. But I mean, same type of thing. This one took like 100 milliwatts in, and I could get about 35 out of it on 432. This is the 902 one. It's a 2 meter IF. I think this one had a built-in attenuator, so I put a watt or 2 in, and it'll do about 12 or so watts out, which is way too much for the amplifiers I have. So there's all of these things have got a little pot in there you can turn down and adjust the output. You also can adjust the input on receive. And where I showed you those dual preamps, I could actually go in on those and turn the gain about as low as it'll go on receive, or I overload them. That's how much gain I got.
So your IF radio to feed these, do you have to go in and obviously modify them to turn down the power?
Nope. Well, you do, but the icon, the first one that I had that I used at Kenwood, and it had a transverter port on it that was like 5 milliwatts out. Okay, and there are some radios that come with low power ports on them. Today I'm using an IC7300 ICOM, and that you can turn the power down. I mean, there's a knob on there, and you can turn it from 0% to 100.
Yeah.
The thing I found though is 0% isn't zero power. There's still a little comes out, but
Maybe like 5 watts?
it's way less than that. It's under a watt. Yeah. And if you need more power, you know, you can put attenuators in the front end of all of these things. The attenuator that's in here it's just like a 25 watt 50 ohm resistor that's bolted. This screw is holding it to the panel. He advises not going more than 10 watts because you can't cool it. There's not enough heat sink there. I have built a couple of other intermediate switches with isolation that'll do 50, and they got great big heat sinks on them and stuff. Well, when Steve sold that stuff off, he sold it to this other guy in Florida, and he calls himself Q5 Signal. He's producing 2 meters, 222, 432, 902, 1296, and you can buy individual band transverters. I wanted to show you this one because this is a product he came out with a couple of years ago. It actually was designed by Steve down East Microwave. This is a 5-band transverter. Okay, it'll do 222, 432, 902, 1296. There's a little band switch here. Or you can access through this auxiliary port and control it with a computer. Okay, front side, back side. You got individual jacks for each band. Okay, transmit side, receive side. You can configure these so you can have just a single common port. Okay, I typically, when I buy them, I do the RF side split, and then you run the preamp in here. That's your second coax. Okay. He makes 2 flavors of this. There's a low power version that does 10 watts on 1296, and it does 25 watts on the other 4. That goes for about $2 grand. The high power one is 25 watts on 1296 and 50 on the others, and that's 2500.
That's a lot of money, but that's a lot of stuff in one box.
It is. If you go out and buy individual bands, you actually spend more. So if you want to jump in with this with 2 feet full force, it's actually not a bad way to go. But yeah, you're right, it is a lot of money. Okay, and I've got single band stuff everywhere. You know, he makes various power models on the single bands, and they're about half this wide. I mean, if you look at the inside of this, there's 5 power modules across here. There's just a lot of crap in this one. The other one's a lot, I mean, most of what's inside the single ones is open air. There's a couple small
Compared
boards.
to that new ICOM,
907.
905?
905.
I know guys that are running them and they like them, but it's a $4,000 radio.
Plus.
You're getting there.
Plus,
Plus.
if you want 10 gig, I think that's another grand that you got to add a separate
I
module.
mean, you're getting there with the IF radio. and
Well,
all
you
this.
are, but you know, a lot of guys have the IF radios already. That's what makes the transverters a nice way to get on VHF. If you got a good IF radio, good HF, you know, with 10 meters, you know, you get up to the microwaves that typically use 2 meters.
Do they really generate that much heat? I mean, when you have the dual fans and the monster heat sink?
Well, considering the power levels, yeah.
Okay.
I've got a 2 meter one that does 150 watts. I bought that. I had to replace my old one, and that one only did 25, and I'm running an 8877 right now on 2. It takes 100 watts to drive. I had to put a brick in between them. When I bought the new one, I bought the 150 watt model because that's more than enough to drive to full output. I'll show you a picture of the amp in a minute.
Remember, Chip, for every watt you put out, you've got a watt of heat. On a UHF
Yeah.
and stuff, it's
Oh, yeah.
even more.
Yeah, 50% is a really good efficiency.
Yeah.
Yes, exactly. Okay, and I wanted to point this out. There's actually, these guys are long gone. There was another outfit out at about the same time, I think it was out of Germany, called SSB Electronic. You sometimes see their stuff. It was really good quality. I mean, this is 70s vintage. It's, you know, transistors and stuff. I mean, it was a shitload of stuff in there, really. Now we're down to 2 U.S. manufacturers, really, down east and Q5. There's also another outfit out of Germany called Kuhn Electronics. Okay, DB6NT was the owner. I think he's recently sold the company, but he makes stuff all the way from 2 meters up through 47 gigs. Really, really high quality stuff. It's a little on the pricey side. I actually have one of his 10 gig amplifiers right here, and it looks very much like that transverter. This is a 24 gig, 2 meters in, it does 2 watts out. This thing, it looks like it's got an external LO you got to connect to it, though. It's not built in. Everything below this, the LO's inside. But this thing, if you wanted one, it would cost you about 850 bucks. If you go on their website and look, it'll show up on their website as 1,059 euros. Okay, but if you look at the fine print, it says including 19%
The VAT.
VAT. Okay, it's basically a European sales tax in the European Union. You don't have to pay that if you ship it here. So about 850. I think I paid 700 and something for that little amplifier.
Right.
Not cheap, but they work. They're really, really high quality, let me tell you. Okay, I wanted to show you this. I had this on that block diagram, but I didn't talk about it. This is a 10 megahertz reference. Back when I got started, all these things used crystal controlled oscillators. They drifted, you know, it's hard to get them on frequency. The other thing you got is, okay, you go up to 10 gigahertz, you don't find a 10 gigahertz crystal anywhere. So you start out at like 96 or 106 and you multiply the living daylights out of it. Well, if you've got a 1 kC error at 96, you're going to have a 100 kC error at 10 gig. I mean, it's going to multiply through the multipliers. About 15 years ago or so, EME, who works for Flex Radio, designed a PLL board for all of these things, and it used a 10 megahertz external reference. There's a couple ways to do it. The first one I built was a really high precision OCXO. The better way to do it, and now you can get these things fairly cheap, it's a GPS disciplined oscillator. These come out of China. You can buy them on eBay. In fact,
$193.
oh, less than that. I think I paid 130 for mine.
Oh, because I was just looking at one today.
Look, keep looking because you'll find them cheaper. In fact, they've got a different one out I've seen now that's about 100. It's a smaller unit than this. Okay, you hook up a GPS antenna and out comes a really stable and really accurate 10 megahertz reference. And if you need more than one copy, this is a splitter, amplifier splitter that Q5 Signal makes. You can also find these on eBay. I think I found an ad for the two of these together. It was like 260 bucks. Down East Microwave also makes a 5 or a 4 output version. I've got a couple of those. And if you need more than one of these, you just cascade them. Okay, you run this into the input, you take one of these outputs to the input of the next one, and you just keep multiplying
You
it.
have that hooked to your signal generator and to your
Well, you could-
everything now.
You could
Yeah,
do
you
that.
can.
I mean, if I had a signal generator that used it, okay. I actually do, but for some reason it doesn't like it. I've got a little older Flex Radio beginner unit that can use it. A lot of the test equipment now, in fact, if you want to try and look at one of those phase lock loop boards, you got to have something that is locked because otherwise you just get noise.
Our new repeater wants one. It wants me to hook one onto it. I don't want to. It's about 300 hertz off, and it'll calibrate itself.
Mm-hmm.
I can do it by hand, but I got to take things apart to do it by hand.
Well, down at the lower frequency, these things will be dead nuts on. I mean, you ain't more than a few hertz off. Up at 10 gig, yeah, you might see a few kcs, but it's better than the 65 kcs I'm off with the crystal oscillator and the one I've got. Okay, and I just wanted to briefly show you some amplifiers. Back in the earlier years, everything was tube-based. I mean, what you could buy back then was a 100 or 200 watt brick, and it really wasn't enough. Today it actually is if you got enough antenna, but back then it wasn't. And you go back in the 60s and 70s in QST and you find all these amplifier designs, and this was one that was there. It uses a pair of keep hitting the wrong button. It uses a pair of 4CX 250s. I know, Brad, you probably are familiar with this. Did you have one of these ever?
I had a Clipperton V,
Okay, well that used a single one of those.
yeah,
Okay.
that one didn't work worth a darn.
Yeah. My first 432 amp was one of these. I mean, this is the whole plate circuit. You got a plate line, there's this flapper capacitor. You can see these two marks of solder. There's actually another little flapper here that's your output that goes right to the output connector. And they're tied to strings that go to these rods, and you just adjust them up and down to tune.
That's just cool.
It's really cool the way it works. And you can get about 600 watts out of this guy. I had a similar one. It was a different design. It was by W2GN, and it actually used a pair of 4CX 300s, which it's actually a bayonet base rather than pins like these. It did a little more power, but same type of layout, okay? This is a Bob Sutherland W6PO 8877. This is what I'm currently running. Bob worked for iMac back in the 60s and 70s. He designed a lot of things
That's
and
a
did
beautiful
notes.
one.
That is really
These are really interesting. They're great amps. I had to rebuild the capacitor bank in my high voltage supply a couple of years ago because they were failing. I actually can get 2,000 watts out of this thing.
I have another tube if you need one.
Okay,
maybe.
good. If you do, let me
I have
know.
a Peter Dahl transformer too.
Oh, let's talk.
I'll never get the project done, I want it to go somewhere.
I want to show you what again, I apologize, this is taking a lot of time, so we may have to stop before we get through a lot of it, but this is what I'm currently running at 432, it's the third amp. Like I said, the first one was a K2RIW, then I built a solid state amp, and I kept blowing the thing up. And I got tired of replacing FETs and boards. And N0AKC, who lives up in St. Cloud, Minnesota, had a whole pallet load of these. I mean, what he gave me was this piece, okay, that's the cavity. Okay, and I had to build up, you know, this is when I built it into frame. There's all kinds of electronics and stuff here. There's transformers for the heater and the grid and stuff, and then I actually used the same high voltage supply as the 8877. This thing uses a Burl, I think it's a 4660. It's similar in size to the 8877, but it's got a coaxial base, and it's actually mounted on its side in the back end here. And you actually have to put a fan out here and suck air through, from here through, instead of blowing in. With my 35 watts of drive, I can get about 800 watts out of this thing. Ron is putting 50 in his, and he says he gets 1200. And he told me that on a whim once he tried 75 watts and he got 1700 out of it. But he said the problem you got there is you can't find relays that'll handle that. Plus it's illegal. But I figure with the 9700 I got now, that'll do more power. I'm going to try that and just see if I can get a little bit more out of it. Okay. Here's one of the solid states. When the digital TV stuff came out, a couple of manufacturers made these high-powered FETs. Things about yay big. It's got a pair of FETs in it. This particular one is rated from DC to 600 meg. The reality is you get above 250 and the efficiency gets so bad they really aren't very good. This is the 220 model that W6PQL designed. Now, the first time I heard about these things was at the Microwave Update Conference, I think back in 2010. They had just come out and guys were building them, and some guys out there showed them. It was a little bit later PQL started making these. And you could either buy a turnkey amp like this for $3 grand, or you could buy kits. Back then he sold kits that you could just buy the circuit boards with all the parts. You could buy the heat spreader and all this stuff. And you know, these were all kits, and you put them together. And I built 3 amp that way for 6, 220, and 432. The 432 has been replaced because of all the problems. But on 6 meters, about 2 watts of drive will get you a kilowatt. On 220, it's about 5 or 6. The problem with these is they don't like, even though they claim they're good to 65 to 1 SWR, the problem is it's not at power. You can't run full power at that. And in fact, what happens, I accidentally a couple of times have keyed it up with nothing connected to it, and you suddenly have a 2,000 watt oscillator. And not only do you smoke the part, but you burn traces off. I mean, I've destroyed the circuit boards. It's a mess, let me tell you. Okay. Well, a couple of years ago, Motorola came out with another one of these that's good up around a gig, and Jim PQL came out. He immediately came out with a 1296 amp. Okay, and he says, you know, this thing will work at 900 meg too, but he didn't build an amp, mainly because the market is small. It's U.S. basically and Canada. Right now, there's probably about 15 guys that are actively chasing EME there. Well, one of my friends in California twisted his arm, and he got him to design this. Okay, and I build these things up to look like the PQL ones. Okay, and here's a view of the inside. Okay, here's your pallet. I mean, today, if you want to buy these things, you got to buy the complete pallet. These boards are pre-assembled. He's got a contract manufacturer. Well, my buddy Ian, who talked him into doing this, found out that his contract manufacturer requires him as a minimum to build 50 board sets. Okay, now that doesn't mean 50 pallets. They're just assembling the 2 PC boards. But Ian felt bad about it, so he bought 4 of them. And plus, I think he bought the full amp he built too. And a couple of months ago, I was struggling. Ian couldn't hear me, and he calls me up on the phone, and he tells me this. He says, if I send you one, can you build an amp out of it? I says, yeah, I've done it a couple of times. He says, okay, I'm going to send you one. It's no cost, it's yours. That's about a $750 piece right here.
$700 worth of copper.
It is. It's a 1/2 inch thick block of copper, and you actually solder this thing directly to it. And that's a trick.
I bet.
Well, I found an easy way to do it.
Heat it up.
Well, you use a
In
piece
the
of
oven.
aluminum,
Yeah.
and my wife has an old electric range with the open, you set that on there
Oh,
and
yeah.
turn it to high till it gets red hot, and you throw that on there, and in a few minutes it heats up and melts the solder. But you gotta hurry up and get it off so you don't overheat the part. Now, I did recently buy, I'm not gonna pass this around because it's, again, a 700 and, where'd I go with it? It's in here.
You lost it already.
Yeah, this is the 1296 version. I mean, it looks very much like that. This one says it'll do 600, it's tested to 640 watts. It's another $750 piece, so if you want to come up and look at it, please do, but I don't want to pass it.
The devices are like $200 or
About
so, aren't
200,
they?
yes.
Yeah, and then the rest is copper.
Yep, yep. Yeah, and then all the parts on there, there's maybe $20 worth of components. Okay.
Stop the sharing, just,
Oh,
Well, we're almost to the end of this section. The one thing I will do is I will pass around. Okay. This is a Toshiba amp that I bought that works at 3.4 gigs. This particular one will do 20 watts out with, you know, like a couple milliwatts in. I have another one that it looks exactly like this, but the front end is different, and it does 50. And there's a guy in Germany discovered after he blew one of these up that if you take and rebias them, you can get 50 out of these. I'm going to try and get on 3.4 gig on the moon with this.
I thought that looks like a part of a Samsung wash machine,
it kind of does.
because I just put one in mine.
you want this pass?
Yeah, that one can be passed.
Okay.
It does work, so please don't go and finger the parts because they're all gas feds. But
That's for moon
Well, maybe,
okay,
you're right.
let's get back to full screen. Now, guys, I want to ask you here because I think we're just about to the end of this half of it, and it's already 9:30, and I could keep going here for a while, but if you don't want to, we can stop. I'm going to leave it up to you guys. I mean, where's the
You
slideshow?
can come back in September.
Just do F5.
F5.
Yeah, I have a real quick question for you,
Yeah,
Charlie.
go ahead.
You get up at power at these, you know, really high frequencies, I mean, there's some safety issues with,
Oh, yeah.
with microwaves and.
2.3 and 3.4 are dangerous. I mean, 2.3 gig is the same frequency as a microwave oven.
Yeah, I know in the Army, we used to test our microwave ops, you know, running klystrons at
Yep.
really high frequencies.
Yep.
Their eyesight failed.
Oh, yeah, yeah. You gotta be very, you don't go look into the dish when you're transmitting.
Right, absolutely.
Okay, I can't remember if it's 2.3 or 3.4, but one of them is the aperture of your eye. So it will, if you run that in your eye, you'll burn it. It's gone.
And we used to pick up dead birds
Oh,
all
yeah.
the time.
Oh, yeah. Yep,
Don't
yep.
stick your head in front of our big dishes on the towers either. They're 34 dB gain
Yeah.
at about almost a watt input to the antenna.
Well, that's a kilowatt of
Yes, it is.
effective
So if you put
radiated power.
If you put a fluorescent tube in front, would it illuminate?
It might.
Probably.
Actually, speaking of that, the first time I was at Dayton, I saw a neat experiment that a guy showed at the antenna forum. He had a little 2-meter Yagi, and he showed how it worked. And he started with a dipole, and you put an incandescent bulb at the center feed point, because that's where max current is.
Right.
Okay, then he had a fluorescent bulb he just held in his hand, and he put it at the center of nothing. You bring it out to the end of the element, and it lights. Cooler, I mean, it really showed how these things were. It was the coolest thing I think I'd ever seen. Really cool. Okay, let's see where we're at. Oh, the other thing I failed to mention, these are 50-volt devices. Okay, and they take about 30 amps at 50 volts. First thing I know you're thinking is high-priced power supplies.
No.
The reality is it's the cheapest part of the system. You go out on eBay and you find these server supplies. Okay, I started with the first ones. I used this one. It's a HB supply, HP, 51.7 volts at 57 amps, and they were selling used 30 bucks. I had a buddy here that wanted one, and I found a guy selling. I got 4 of them delivered for 100 bucks. So I got 3 spares sitting out in my shed. Okay, this one uses 220 volts. This one I just found out about. One of my friends turned me on to it. It's a flat pack. This one runs off 110, and I needed that because on my microwave stuff, because I'm so far from the shack, everything but the I-up radio is out at the dish. So I got 110 volts out there, but I ain't got 220, and I don't want to trench it in because it'll cost a fortune. This thing works great. It says 48 volts, but if you look at this tag up here on the top, it actually says it's 53.5 at like 37 amps. It more than powers the...
Because they're still running 48 volts in the supercomputers.
Are they?
Yeah.
Well, whatever it is, it's somewhere in the 48 to fit, but I mean, it delivers enough. I can get 800 watts.
Do you want one, or?
I don't really need them.
Okay.
I mean, unless you got one of these, I'd take it. But I do want to get another. I paid $50 on eBay for that. They got a 3,000 watt model too. It's 50 some amps. I think those were going for 150, but really, like I said, cheapest part of the system. Okay. All right, well that gets me to the end of this. I could probably go on for a lot longer here. If you prefer that I stop because it is getting late, we could break here. And if you'd like me to come back, and the rest of it is building my station and some of the stuff I've done. You know, there's
Do we have September open?
That's pretty good.
Because August is gonna be a little.
Yeah, we won't do
busy here.
August.
Well, if we do
Whenever it fits, we'll figure something out.
Okay, this is really interesting.
September would
Well,
be
I hope
good.
this is a little more interesting than the first time. I mean, you're learning a little bit more on what do you do to build. The rest of this, what I want to show you is what I went through building mine and why I got involved
Yeah,
in EME, because that's kind of a neat story, and there's a backstory to what really finally pushed me into it that is in this. The other thing it might do is it might allow me to maneuver this a little bit more and
yeah,
put a
okay,
few more things in it. So if everybody's okay with that, let's just stop here.
okay.
I apologize it got long, but there's just so much stuff to cover. And there's still a lot more. I mean, I could talk here for probably a couple more hours on stuff and bore you to death. At least everybody stayed awake.
Didn't you do or go to a presentation out east?
I'm going.
Oh, okay.
It's actually the same weekend as your
Hamfest,
Hamfest.
that's right.
Okay. The Central States Conference comes first. I'm actually on the board of directors for that organization. They have a conference every single year this year, and it moves around the country. Central States basically is from, you know, central provinces of Canada to Texas. And,
Okay,
but they get people that come from all over the U.S. We get guys come from overseas. You typically get 150 people or so show up for a couple of days, and there's presentations. I've given presentations there. I'm giving one at that's the end of August, or end of July, and then 2 weeks later is EME, and then
okay.
October is the Microwave Update Conference. I'm going to that this year.
That's better than field day.
I gotta go. It's almost bedtime. Thanks, Charlie.
Yeah.
Yeah, this is really good.
Well, I guess I should ask, is there any quick questions that haven't already been answered?
Do you play satellites at all?
I've done it one time.
So that's
Very briefly.
Pretty boring compared to this.
Well, the problem I had is I was using the EME array.
Oh, geez.
That was the uplink, and there's 2 rotor controls, and you gotta constantly keep moving
Yeah,
it.
yeah.
Plus, the receive antenna was on a different tower, so that was the 3rd rotor. And I did it, I made about 3 or 4 contacts, and it was fun. I'd like to do it again, but I would have to have a dedicated system for it.
Gotcha.
Did you have something else, Brad?
Yeah, I mean,